of Newton for me is really a great honor, so I would like to thank the organizers for these. So while we are at it, molecular dynamics simulations try to estimate the macroscopic anisotropic behavior of liquid crystalline models, as I said before, by solving Newton's equations of motion. So they take the positions and the orientations of the anisotropic particles, and then compute numerically the time trajectory of these particles, and so they produce a huge collection of positions and orientation of the molecules in time, and from this information one can compute all kinds of observable and structural properties. Monte Carlo simulations do more or less the same. They also produce a huge number of these configurations, but instead of solving a set of equations, they perform some sort of random sampling of the Boltzmann distribution. They can be used for all kinds of models, so they can be used going from the very idealized lattice models where mesogenic particles are represented as spins. On the other hand, you have the so-called atomistic models that are the most accurate ones in terms of molecular structures, and in those models all atoms are taken into account explicitly. In between these two extrema, you have the so-called molecular or coarse-grained off-lattice models, where particles are approximated by simple geometric shape that try nonetheless to take into account the features the real mesogenic molecules might have. And these models are interesting because even though they are very simple, they still get all the phases you expect from this sort of nematic systems. And since they are simple, they allow you to draw a bridge very clear between the specific properties of these simple models and the macroscopic behavior. So this is an advantage, but at the same time it is a disadvantage, because when you talk with the synthetic chemistry and try to reverse engineer your model, you know exactly how the model behaves, and you want to answer the question of a chemist. So how should I build up a molecule which will have this kind of properties? To answer this question is very difficult. So typically performing simulation amounts in fulfilling or performing these 4 steps. The first step is the one of choosing a model, define the properties of the particles, so what is their shape, how they interact in pairs, and so on. Once this part has been accomplished, one can prepare a virtual sample of these particles in the memory of a computer, and then perform a virtual experiment running one of the standard Monte Carlo or molecular dynamics algorithms. Those produce the configurations that can be analyzed. So in my talk, I will spend most of the time talking about pair potentials in here, and then I will present some results in the final part of the talk. In the previous talks, we have already seen why these hard particles models are very important. They are able to grasp all the fundamental physics of liquid crystals, and they allow to draw a very strict bridge between the computer simulations and the theoretical calculations. So we have already heard a lot about the mesogenic properties of sphere cylinders, and also ellipsoids have been studied in great detail, both elongated, like in this drawing here, and also symmetrically with respect to this phase diagram, having disks that are very wide and thin that produce nonetheless nematic phases. This is the phase diagram for uniaxial cylinders, but also biaxial ellipsoids have been studied. In this case, the 3 axes of the ellipsoid were different, and the biaxial nematic phase was observed. So one thing that all these kind of simulations have in common is that there is a moment while performing the simulation that one needs to know if the ellipsoids are touching one with another. Imagine, for instance, a Monte Carlo simulation. You have one particle surrounded by the other ones, and then you are performing a random displacement and rotation of this molecule, and you want to know if this is touching other ones. So in principle, from a mathematical point of view, if these are ellipsoids, one can write the equation for these functions. You know exactly how they are, where they are, and so one could compute the contact distance starting from this piece of information. So it is a very well-defined problem, but in practice is a very tricky one, and well, we can just quote the author here in the front row. Well, it has no analytic solution, and the first complete algorithm solving this problem has been published 4 years ago. So how could the pioneers in computer simulations attack this problem maybe 40 years ago? So they used some sort of alternative way. I mean, they didn't really compute the contact distance, but they could set up some sort of what is called an elliptic contact function that solving the quadratic forms of the equations describing the ellipsoids simply tells if it is larger than 1 if they are not touching, if it is equals to 1 if they are tangent, or if it is smaller than 1 if they are overlapping in some way. So this is one solution, and then, as I told you before, this paper in 2009 was published solving finally, eventually, the problem. But unfortunately, at least as far as I know, this algorithm has not been used yet in computer simulations, possibly because the correct or exact computation of the compact distance is computationally expensive. So back in the years where there was still no algorithm, another approach was published, and this approach was due to Bruce Byrne and Philip Pechoukas that used this sort of idea. They overlapped or added on top of each ellipsoidal particle a Gaussian function with the same standard deviations, or at least with standard deviations of with the same length of the molecular axis of the ellipsoids. So each ellipsoidal particle bears a Gaussian function on top of it. This can be written in terms of this diagonal S matrix that contains the lengths of the molecular axis of the standard deviation. It is squared, then it is rotated in the laboratory frame and translated in the position where the particle is. And once one has these two Gaussian functions, one can compute the overlap integral. This integral is still a Gaussian, and it can be written in a compact and nice way, defining this sort of overlap matrix where the two quadratic forms obtained rotating the diagonal shape matrices are summed up, and the final result is that this overlap integrals, the integral depends on the determinant of the overlap matrix and the exponential of this quadratic form. And this quadratic form here can be used to compute this approximated constant distance obtained considering the overlap of the two Gaussians. So this equation here is very fast to compute and also easy to code, and it works reasonably well. But there's a but, because this approximation here doesn't work if the Gaussian functions are very different, but as long as you perform a simulation using a pure system of similar particles, or a system where the polydispersity or the differences between the sizes of the particles is not too much, this is not going to be a problem. So this contact function was used in 1981 by Bruce Byrne and Jack Gay to set up and create what has now become one of the standard models for mesogenic particles that now bears their name and is called the Gay-Byrne model. It is some kind of anisotropic Lennard-Jones potential that I will describe later. But first, I would like just to tell you something behind the story of this potential, because when it was made, certainly Bruce Byrne was already a very famous physicist, and for some reason he was contacted by General Motors. Where is it? Well, it was contacted by General Motors because it seems they were interested in doing some sort of fundamental research on liquid crystals. And the liaison scientist that was to keep the contacts between General Motors and Bruce Byrne was Jack Gay, who was by education a solid-state physicist. And I don't know exactly how this collaboration went. Eventually they published this paper, and I think that was the end of it, because nothing else came out from this collaboration. In spite of this, this potential became quite famous, and I think the last phrase by Bruce Byrne, it's really interesting, because I don't think that Bruce Byrne considers this potential one of his most remarkable achievements, but in spite of this, it has become extremely popular, and I think he will have to live with it. So it has been so popular that a large number of people have started fiddling with it, changing it, modifying, and so on. And also we did something along these lines, and our small contribution was to generalize the potential from the description of the interaction between uniaxial particles to the case of biaxial particles, where the ellipsoids have three different axes. So here you have, for instance, the three representative interaction energy curves for the face-to-face, side-by-side, and end-to-end interactions. So now I'm going to show you the expressions for this kind of generalization, but later on I will also quote other forms that can be used, that can be interesting for simulations. So I told you before that the Gay-Byrne potential is an anisotropic Lennard-Jones. So you can see here the two terms, the one where the intermolecular distance depends on the inverse 12th power of its value, and this represents the repulsive barrier one has for short separations. Then there is the other term which has the same mathematical expression but has a 6th power exponent and there's a minus sign in front, and this represents the attractive branch of the potential arising from the dispersion interaction between the particles. This is an isotropic, so we have two functions that depend on the separation and its orientation R, and the orientation of the two molecules that here is represented with this boldface Q. This sigma here is exactly the Gaussian constant distance that we have seen before, and this is X expression, and this is obtained, as I told you before, rotating these diagonal shaped matrices using the Cartesian matrices giving the orientation of the molecule. In computer simulations, it is very convenient to use quaternions for describing the orientation of the molecules, both because they are very efficient in doing this, and also because the solution of the dynamical equation for the rotational motion are free from singularities. So at the moment they are extremely valuable, very invaluable for simulations, and it's a bit of contrasting the fact that now they are really recognized as very powerful and interesting, but they had a very difficult start at the beginning when William Hamilton and Olind Rodrigue developed them independently. So this is a very nice paper story to read, just to have an idea of what went wrong at the time and was corrected only maybe 70 or 80 years afterwards. But coming back to the Gaborian potential, there is another anisotropic term that modulates the depth of these interaction wells, and here it is. This is a bit more complex. There's a scale factor and then the product of two anisotropic terms raised to two exponents that can change the features of the potential, but not the physics, essentially. They only change the range of temperatures one observes certain phases. And the first term is the last piece arising from the Gaussian overlap we have seen before and depends on the determinant of the shape matrix. And the second part is instead mathematically similar to the sigma function we've seen before, but this time the diagonal matrices that provide the properties of the particles are parameterized in terms of three parameters that are proportional to the depth of these interaction wells. So using these expressions, one can use the potential both in Monte Carlo and molecular dynamics simulations. For the molecular dynamics simulations, one also needs the derivatives, so the gradients and the torques of the potential. These have been published, so it's everything is ready for doing the simulation work. And since the publication, there has been a tremendous amount of work made by a number of people in the field. The model shows all kinds of liquid crystalline phases, so nematic, osmetic, columnars, just you name it. And for instance, here you have, these systems have been studied really in detail, and De Miguel, De Rio, Allen, and Brown have published a number of papers just giving in detail the phase diagram for all this family of models, changing the shape and the interaction properties. And they also published more or less at the same time we did a Baxial version equivalent to our one for the Gaborian potential. And more recently there was some work trying to overcome the problem related with the usage of the Gaussian contact function that doesn't work well where the particles are very dissimilar in shape. So there are at least these two papers. In this one, Evrares and Echardi tried to generalize the Gaborian potential using an approach based on the Hamaker theory for colloidal particles. And in this one, Yaliraki and Paramonov did something similar, trying to use instead the contact function developed by Perram and Wertheim in the 70s. Since we are in a mathematically oriented environment, I would like now to talk about something that usually I do not do, and regards the integration, the numerical integration of the rotational equations of motions. Usually people who do simulation do not worry too much about these issues because the algorithm have been developed many years ago. They've been thoroughly tested, so the integration algorithms are reliable and robust, and they have all the nice features you would expect from them. Nonetheless, if you look at the papers that still continue appearing of people just suggesting new modification and changes, I believe maybe there is still time and still scope for improving the existing algorithms. So I just would like to highlight one of them just to give the feeling of the problems and the kind of computations that are typically performed. So in this case, we want to compute the dynamics of the rotational motion, and the force that changes the orientation of the molecules is the torque, and the torque formally can be computed from the energy of the particle, applying on it the angular momentum operator. And the algorithm, this operator can be written in many representations, and since we are using quaternions, we can also derive a quaternionic representation for this angular momentum operator. Once we have it, we can combine these equations with the kinematic equation of the rotational motion that links the angular velocity of the particle with its orientation to give the time derivative of the orientation of the particle. And then we can plug together these pieces to obtain two additional operators. One is this one, and this operator, using a Liouville description of the dynamics, performs the time of evolution of the orientation. So in this case, this expression here can be approximated to first order to the rotation of the quaternion plus the first order term that gives the value of the orientation after a time step delta t. This second kind of operator can be used to do something similar, but in this case for the angular momentum. So these two expressions can finally be used to develop some sort of velocity Verlet-like algorithm for the rotational motion, and typically one first evolves the angular momentum from a given time to a half-time step forward. From this value here, one computes the orientations and the time derivative, and these are used to perform a full-time advancement of the orientation of the particles. And once one knows the orientations at time t plus delta t, it is possible to compute the new torques. And knowing these torques, one can also advance the angular momentum at the final position in time. So this is the kind of algorithms that are used typically in computer simulations for solving the equations of motion, and they work reasonably well, but maybe there are still possibilities for improving them, and so maybe this is the right audience to just give the question. So this more or less closes my first part of the talk, and now I would like to just give you a feeling of the things we can do with this kind of potentials. And in this case, I would like to present you the results of an additional generalization of the Gaborian potential we have made with Mark Wilson. And the idea was to replace the repulsive barrier, which is described by this r to the minus 12th term in the Lennard-Jones potential, with a gentler slope that would allow the particles to become closer together without paying a very high energy penalty. And this would mean like studying fluffy molecules. And this kind of systems can be interesting both for liquid crystals, but also for polymeric systems formed by molecules that are very flexible. And I give you here an example, still in the liquid crystal field. This is a very large molecule. You have 4 of these very large and flexible pieces attached to a central silicon atom. And this molecule has been shown in 2004 by Georg Mell to form a Baxian nematic system. And so the question is, why is this molecule forming a Baxian nematic system? So I think we can have two different interpretations for this kind of mesogenic behavior. The first one is certainly related to the forbidden word that Dan Frankel highlighted before about polydispersity. Since this molecule is very flexible, it can change shape very easily. So you can imagine a solution of this model, this molecule, like formed by a collection or a population of molecules that have a different length, width, and depth mixed all together. On the other hand, you can consider this molecule as some sort of a fluffy one because of its possibility of changing shape. And since these fluffy particles can interpenetrate one into each other and maybe stabilize the phase biaxiality against the formation of layered structures. Another family of systems where these soft core potentials can be applied are those where depletion interaction appear. For instance, one could have a colloidal particle with an external layer of flexible spaces that would change the repulsive branch of the potential from a very steep one to a more gentler slope. And the idea for this potential was generated by this work of Mark Wilson when he used this coarse-grained model based on soft core, soft ellipsoids to study effectively the mesogenic properties of this kind of huge octopus-like molecules. So the way the potential is modified is that of seaming in a continuous way the Gay-Bern potential with a linear function of the distance by means of some sort of blending or seaming function. This function is a smooth sigmoidal function that changes continuously from 1 to 0, and it is centered around the place where the potential energy is 0. Now, just before showing you the results of these simulations, I need to introduce a couple of other parameters. The first one we have already seen is the classical Mayer-Zaupe order parameter, and this morning was represented with an uppercase Q. Often one has uppercase S or P2 because it's the second Legendre polynomial, or sometimes one has even this more complex notation, and it gives the average orientational ordering of the long molecular axis that usually it's labeled Z with respect to the principal director of the nematic phase, which is N. So this is enough if one has a uniaxial phase. On the other hand, if one has biaxial particles and possibly a biaxial phase, one could also be interested in measuring the average orientation of the transversal molecular axes Y and X with respect to the transversal secondary directors of the phase M and the one perpendicular to it L. So one can define a suitable second biaxial order parameter that has this sort of expression. So now we have the order parameters. We can perform the simulations, and in these pictures I'm showing you the temperature dependence of the, in this case, uniaxial order parameter for a system of uniaxial Gay-Bern ellipsoids, and I want to compare the results one gets for the standard Gay-Bern model that corresponds to this curve here, and compare these results with those one has when the potential becomes gradually softer and softer and softer. So softness has two kinds of effects. If the slope of the repulsive branch is not very far from the slope of the original potential, which means that the particles are a bit soft but not too much, this greatly enhances the mesogenic properties of these systems, and the phase transition shift towards much higher temperatures compared to the standard system. On the other hand, if the particles become very soft, they can compenetrate effectively each other, and this destroys all the entropic effects arising from the excluded volume we've seen before. So if they become very soft, this second contribution destroys the first one, and the phase transitions move to lower temperatures, and eventually the nematic or all ordered phases completely disappear. So this can be perceived in this graph where we have these vertical lines. This is the isotropic nematic transition for the standard model. This is the nematic osmotic transition for the standard model. And we want to concentrate on these green dots represented in nematic phase. So you see that changing this parameter, scantily soft, softer, even softer, extremely softer, we can change the temperature range of stability of the nematic phase and also shift it a bit towards lower temperatures. Softness also affects the structural properties of these systems. The positions of the maxima of the radial correlation function are not greatly affected, only the height, but the place where there are larger changes are the distances corresponding to the strong overlap between the particles, and for the standard model the function here is practically zero because this histogram is practically not populated. But as the particles become softer, some pairs of molecules start arriving at those distances, and progressively the histogram becomes more and more populated also in this area here. We have also tried to see what happens when one introduces a softness in a baxial system. Here you have just a cartoon showing a baxial nematic fluid formed by ellipsoidal particles. Now I will skip a bit of these transparencies. So we used a parameterization we studied some years ago with the Gaborian potential, and we added to our particles a certain degree of softness. So the first result was that softness was not incompatible with phase biaxiality, and maybe it's better to again look at the phase diagram. In this case, I want you just to take notice of the blue squares, and this line, this line here is the uniaxial nematic, biaxial nematic transition for the standard model, and just close here there is the transition to biaxial osmotic. So the idea is that again, using the softness, one can shift and enlarge the range of stability of the biaxial nematic phase, and most importantly, it can be shifted to very low temperatures where the standard system would be already an extremely highly ordered biaxial osmotic phase. And this is a real problem because apart this kind of molecules here that are biaxial osmotic at room temperatures, the known biaxial nematics usually have this sort of band core shape, and they form the biaxial nematic phase at very high temperature, I mean around 200 degrees Celsius, And using this kind of materials at those temperatures is not really convenient for technological application. We want to have computer displays working at much lower temperatures. So I would like now just to spend a few minutes talking about the another kind of Baxter systems. In this case, a mixture. And the idea started many years ago, and Richard Alben suggested that a way of having a Baxial nematic phase could have been that of mixing rods and disks. They would align along mutually perpendicular directions, and so they would form a Baxial nematic phase. Things proved to be extremely more difficult because both from the theoretical point of view, experimentally, and also in computer simulations, when the density increased or the temperature was lowered, one would have phase separation. So the first positive result was made by Jackson, Galindo, and Quetus in 2008, and they were able to stabilize a mixture of biaxial rods, uniaxial rods and disks using a weakly binding interaction between the hard particles. Another important result was, or suggestion was given by Fotinos, Bayes, and Vanakaras that suggested how to choose the shapes and the dimensions of the particles, and I will just tell you how in a few transparencies. And then there was a theoretical experimental result by Georg Melg, who was able to synthesize an entire family of molecules which have a discotic and an elongated shape that were entirely miscible completely miscible in the entire nematic phase. So it can be done. It didn't observe Baxian nematic phases, but it didn't observe the mixing either. So in our case, we performed a simulation of a mixture of biaxial ellipsoids, and using the suggestion of Fotinos, using particles which had a pair of axes with the same length, but the remaining two with incommensurate lengths, and this was aimed towards destabilizing the formation of layer structures, and parameterizing the interactions in order to have side-by-side interactions stronger than face-to-face and just going forward. We were able to obtain a mixed system that was fully miscible in the entire nematic range, and also formed a biaxial nematic at a very low temperature, where the system of pure rods would already be in an extremely ordered biaxial symmetric phase. And so this is the main result from these simulations, and one can see that there is this region where the biaxial nematic phase is stable that has been shifted with the mixture to low temperature. So maybe this could also be a practical way of having room temperature biaxial nematic phases. So now I gather I'm really running out of time. I'm skipping. Oh, well, first I would like to mention Chandrasekhar, because the model we used to study this system boils up in just a practical realization of what Chandrasekhar already envisioned in 1985, and that molecules showing a biaxial nematic phase should have some sort of dual behavior that mixes the behavior of a rod and a disk. So now I will skip completely this part. There will be a poster, and possibly also Claudio will talk about it later in the week, so there will still be a chance for talking about it to those who are interested. I would like to just make a final comment about other parameters, again, because here we are within mathematicians. And what is my comment? Well, from a macroscopic point of view, order parameters can be obtained considering the anisotropy or specific macroscopic anisotropic properties of the system, for instance, magnetic susceptibilities or refractive indexes. On the other hand, in computer simulations, we use a bottom-up approach, and in this case, we compute tensorial properties starting from very specific molecular properties, and considering the ordering matrix we have already heard this morning, we can use as properties the orientations of the X, Y, and Z molecular axes in the laboratory frame. The reason why here there are 3 ordering matrices is that if the particles are biaxial, there are 3 mutually orthogonal directions that we want to keep track of. So we have 3 ordering matrices, and if we consider in a formal way the transformation from molecular property to director frame, one has to use some rotation matrices, and eventually averaging and symmetrizing with respect to a certain symmetry of the molecules and the system, one can end up with explicit relationship linking the properties measured with respect to the director to the property one knows from the molecule, and the coefficients that perform this transformation are the other parameters. So for instance, here we have the 4 symmetrized second rank order parameter for a D2H system, and the first one and the fourth one we have already saw before. So how one does the computation of order parameters in pure systems? Well, in pure systems, one has 3 ordering matrices, 1 for each of the molecular axes, and they can be computed summing up the contributions of all the molecules in the sample. Once one has these 3 matrices, one wants to diagonalize them, and in principle one would expect that these had the same set of eigenvectors, but as it comes out, it is not always so, because they do not exactly commute. So the best thing we can do is try to simultaneously diagonalize them until the sum of the squared of diagonal elements is minimal. For instance, one can use some sort of Jacobi-like rotations to do this. Once these eigenvectors that are common to the 3 matrices have been found, we still have to decide which one is the principal director and which are the other 2. And so we have to label them, and we can follow some sort of standard procedure looking for the labeling that gives the highest Meyer-Zaupe order parameter and the smallest possible biaxiality. And why I'm telling this to you? Because this algorithm now works reasonably well. It's established for single system components, but if we go to systems where there are more than one species, things are not any longer clear, and at the time being there is no algorithm for computing a global macroscopic order parameter similar to what one does experimentally, just measuring a refractive index. So we try to do something for the mixtures of the biaxial ellipsoids I showed you before, but this algorithm is certainly far from being complete or entirely satisfactory. So I believe that the computation of other parameters in computer simulations, maybe polydispersed systems and these sort of things, is still something that it is missing, and it is something that requires more work to do, and I think that maybe this is the right audience for raising the problem. So this is my last transparency, so I would like to thank again the organizers and you for your attention.
We don't really have much time, but maybe 1 or 2 questions if there are. don't have questions, we can go and have the photograph taken.